Okay, our final speaker today is William Ceely. William got his bachelor's degree in electrical engineering at University of Central Florida, got a master's from USC, also in electrical engineering, and he's currently working on his PhD at Claremont Graduate University with Professor Ali Nadim and myself. We've been working for a few years, and he's also very close to finishing up his PhD work. I wanted to just introduce this by saying that we've heard about a lot of biological aspects of the glycocalyx and the glycosaminoglycans, the electrostatic interactions, and so forth. I wanted to do a quick thought experiment, which is going back to your undergraduate biology or biochemistry classes when you first saw a semi-permeable membrane, and we applied some counting of charges on the two sides of the membrane. So sodium and potassium on two sides of a phospholipid bilayer could result in an electrostatic potential across a membrane. But if you imagine now that one side of the membrane has fixed charges, shouldn't we expect the same sort of thing? And isn't a glycocalyx, doesn't it look like a region of fixed charges? So the sulfates and carboxylates look like a region of fixed charges, somewhat fixed on a short time scale. And so a model for this that we've developed over the years has been that of a polyelectrolyte brush. So from a polymer scientist perspective, the glycocalyx looks sort of like a polymer brush. And if you look at those pictures that we've seen today, the images all essentially look like a brush. And so that's where the starting point is. And now we're going to have a look at the biophysics of what looks like a glycocalyx model as an electrostatic interaction. So, William.
All right, thank you. So he gave, I'll be able to shorten up my introduction a bit due to some of his explanation. And I know we're behind time, so I'll try to just get to the meat of the presentation. But quickly here, we have this GAG region, and then we have a salt region. And this GAG, well, it can be really any type of macromolecule, but for the sake of this, we looked at a GAG anionic brush, which is essentially a model of a glycocalyx with a uniform negative charge, where other molecules or ions can bind to it to provide electroneutrality. But in this case, unlike some of the other presentations, there's no chemokines. I'm only considering ions. And the goal was to develop some mean field mathematical models to describe, the electrostatics that are occurring inside this system. So I mentioned GAG. The one I'm looking at in this presentation is hyaluronic acid, and the salt is sodium chloride. I'm going to skip this slide just for time, just of why using continuum, and just to go straight to the model. So the steady state model is a modified Poisson-Boltzmann model. And so you start off with the Poisson's equation on the first line. And on the right-hand side, you can describe the cation and anion concentrations. They follow essentially a Born-augmented Boltzmann distribution. So here's your electrophoretic term inside the exponential here, and here's your Born term. I'll talk a little bit more about those in a minute. And then the brush concentration, the unbound brush, has this term here, which is to incorporate what we call ion pairing, or the binding that we are allowing to occur between the cation and the brush. Just for complete mathematical sake, zero surface charge density boundary conditions, and this is what we consider a second order nonlinear ordinary differential equation. So moving on to the ion pairing, to how I got the expression for the brush concentration. Essentially, start off with the reversible reaction at equilibrium. We have the forward reaction rate times the concentrations equals the backward reaction rate times the bound concentration. So if we solve this for the bound concentration, and we can define this capital K, which is the dissociation constant, it's just the ratio of the backward reaction rate over the forward reaction rate. Like I said, we get this expression for the bound concentration, and knowing that the total brush concentration is constant, we can represent that as the sum of the unbound and the bound, and we can stick in this expression for the unbound for the bound concentration, and then solve for the unbound brush concentration there. And then on Born, it was proposed by Max Born in 1920. Just a bit of trivia: he was the grandfather of Olivia Newton-John. So basically, what the Born energy proposes is that the expression is here. Lower permittivity leads to higher energy. So you can see the permittivity is in the denominator, and also there's this this radius, a Born radius. It's not a physical ion radius. It's just to make sure that's clear, it's not the physical radius, and because of that, actually we see that the chloride Born radius is like 10, a magnitude of 10 less than the sodium Born radius. But essentially, mobile ions are going to want to move to regions of higher permittivity in order to minimize this energy here. And so in some molecular dynamic simulations that I used as inspiration, the results showed that the permittivity was lower in the brush region than in the salt region. And in fact, it was within the brush region, you could consider it constant. And then within the salt region, it was also constant. And so the transition between the two really occurred at that brush salt interface. And so that's really where the Born force is acting. And so because of that, we modify the typical Boltzmann distribution to get the modified Poisson-Boltzmann model. Now, a little bit on we have a transient model as well. And I know I could have started off by displaying this, because really you can derive the steady state model from this transient model if you assume you're at equilibrium. But we have the Poisson's equation, but instead of fixed expressions for the concentrations, they're replaced with time evolution partial differential equations. So some of the key things that I just want to highlight is, so the cation and anion, we have this diffusive term. And so the diffusive term essentially is going to regions of higher concentration. It's going to want to move those ions to regions of lower concentration. And then we also have two force terms, the electrophoretic force, and we note that they have opposite signs for the cation and anion. So what that shows is if there's a gradient in the potential, the cation is going to want to move towards regions of lower potential, and the anion is going to do the opposite, move to regions of higher potential. And then again, we have this Born force term, and as I mentioned, it's mostly acting right there at the interface, wanting to push ions of any kind, so both positive or negative charges, from the lower permittivity to the higher permittivity region. And in the cation expression, we also have the binding, and the signs are such that obviously if the unbound cation is binding to the brush, the concentration is going to decrease. But if there's unbinding that's occurring, the concentration will increase. And you can see the expression for the bound cation and brush concentration has the opposite signs. And again, zero surface charge density and zero ion concentration flux boundary conditions. And here we have a system of nonlinear partial differential equations. But as I mentioned, if you assume the time derivative for 0 for each of these, which is at equilibrium, you can show how this basically simplifies down to that single ODE steady state model. Okay, now on to some results. So here's some initial conditions I looked at. First, I want to highlight that the conditions here are not physically realistic. Instead, it's starting off this system very far from equilibrium. And the main purpose for doing that was so that I could get a good glimpse of how each of the diffusion, electrophoresis, Born force, and binding terms, impacted the concentrations at the different time steps. And so I started off uniform concentration of sodium and chloride, and the completely unbound brush And the total charge within this system is 0. So we have electroneutrality throughout the whole region, but clearly when I started off, it's nowhere locally electroneutral. And this initial potential is, I didn't specify that, but rather use the first equation on the previous slide and solve, using these initial concentrations. We see that we have a large gradient, and it's very negative, or in the brush side. And so now to describe a little bit about what's going on. So because I chose to uniform concentrations, there's no diffusion happening initially. But with this large gradient and the potential, we see that the electrophoretic force is going to want to move the sodium ions from right to left. So from the salt region to the brush region. And then conversely, for the chloride, it's going to want to move those from the brush region to the salt region. And then the Born force is going to act right here at this interface, and it's going to act always from left to right. Want to move ions from the brush region to the salt region. But as I mentioned, the Born radius for chloride is 10 times smaller than the sodium Born radius, and therefore the Born effect is like 10 times as large. So it's stronger on the chloride than on the sodium. And because I started this off completely unbound, there's no unbinding occurring initially, but we do start to see some binding. And so based on how those different terms interact, what we see, if we focus first on just this dotted blue line, which represents about 0.005 nanoseconds in, we see that there's an initial slight increase in the sodium concentration in the brush region, which was expected if electrophoresis is moving those ions from the salt to the brush. But because of the Born force, we see there is a little decrease right there at the interface. And then overall, there's a net decrease in the salt side. Now for the chloride concentration, there was a net decrease in the brush region, more of a decrease right here to the left of the interface, and an increase to the right of the interface, and then an overall increase on the salt side. And as I mentioned, some binding starts to occur. So we see that the bound concentration increases slightly, and it's not necessarily completely noticeable here, but this did decrease slightly. Now, as time progresses, these these interactions get very complex. And to really appreciate what's going on, I would need to show you probably 10 other figures and look at them all at the same time. But without that, I'm going to try and just describe things one at a time. If we focus on the potential, we see, oh, sorry, let me take one step back. I want to just state that if you look at the timestamps, basically there's most of the action occurs within the first 10 nanoseconds. And then from about 10 nanoseconds all the way to when it reaches equilibrium at around 190 nanoseconds, things slow down and everything happens much slower. But if we look now at the potential, we see that over time, it's starting to increase, but there's still a large gradient and much lower potential on the brush side. So the electrophoretic force is still acting in the same directions as it was previously, but the impact of it is decreasing with time. And in fact, there is a time when the potential actually becomes positive in the brush side, and therefore now it's going to start switching signs. So at that point, it's going to want to drive the sodium back out of the brush region and into the salt region, and then conversely try to attract the chloride ion into the brush region. However, due to Born force, the chloride, you'll see, kind of pretty much is completely evacuated from the brush region. And we can see that it does overshoot the steady state and eventually settles back down to the steady state. But one thing that's curious is, as it goes back down to steady state, there's this sort of this peak right at the interface in the potential. And so electrophoresis then at that point, right there at the interface, wants to move sodium ions, to either side of that interface, but push chloride, if there happens to, which there isn't at equilibrium, but any chloride that still exists in the brush side wants to push it towards that interface, and then on the salt side wants to push it towards the interface. If we look at the binding terms. So we'll focus on the unbound brush and the bound brush concentrations. We see that overall so both binding and unbinding can occur at the same time, but what happens is that binding is happening much more rapidly, and so overall you see a net binding effect. And at these time steps, you could see how quickly the unbound brush concentration is decreasing. And in fact, we actually, the ion pairing actually overshoots the steady state, and you get more bound concentration, and then it eventually switches to a net unbinding scenario where it unbinds down and approaches back to the steady state. Now, if we focus on the different concentrations, you can see that the diffusion story is going to get very complex really fast. So it starts off, now that we have no longer a uniform concentration, we see that the diffusion is going to want to decrease right here in the brush and right here in the salt, and increase right here at the boundary. And now, like I mentioned, all these things are occurring at the same time: the electrophoretic force, the Born force, diffusion, and binding. And so which ones dominate in which regions are not necessarily apparent just by looking at these time slices. But again, I would have to show a lot more figures to get that full story. But as time progresses, you can see the diffusion is gonna increase in strength. Right here, there's gonna wanna be diffusion towards the interface. And then eventually, when you get to about 6.5 nanoseconds, we see that, again, there will want to be some diffusion towards the interface, but there'll be diffusion also into the salt region. And again, here, while binding is occurring, there also wants to be some diffusion of the sodium from the boundary of the brush towards the interface. With the chloride, the Born is pretty much the predominant term throughout the whole thing. So even though there wants to be diffusion occurring inside the brush, but the Born is essentially forcing all of the chloride out of the brush region. But the diffusion does occur on the salt side, and you have this initial overshoot right here, just to the right of the interface, and eventually that diffuses at steady state to give you a nice flat chloride concentration. Let's see, what time are we at? 2:38. Okay, so I'll jump to a plot of the steady state. So it's not necessarily apparent to us here, but I've overlaid the equilibrium solution from the transient model with the solution to the steady state model. And you can see that within numerical computational accuracy, they agree, which was expected. But it's good to see that that's the case with the two different models. And so just to highlight here, it's a more zoomed in image. You can see that you have this region where there's a higher potential right there at the interface, but in the brush, we have overall higher potential on the brush side than on the salt side. So we have a positive, what they call a Donen potential. Now at steady state, I just want to emphasize that it's not that binding stops or Born force just gives up and electrophoresis quits, but it's all these things cancel out, and they just so there's zero net change with respect to time once we get to the steady state, but all these interactions are still occurring. So just in conclusion, I developed a steady state and transient mean field models for GAG brushes. They incorporate ion pairing and varying permittivity effects, which results in the Born force. And the transient model does approach the same equilibrium solution as the steady state model. Now, even though this model was specific for GAG brushes, it is easily extensible to include other types of macromolecules, multiple macromolecules, and even more cations and anions of varying valences. Model parameters, I didn't go into details on what the values were, but they were chosen to fit the molecular dynamics simulation data at equilibrium. And so, hopefully that these models can be useful to somebody in some extent in this audience. And give a good biophysical detail of biological environments of interest. But with that, I'll wrap it up here.
Yes.
Mhm.
Is there any experimental models that you're aware of? They probably can't give you sort of the micro, but they can at least give you the macro of the potentials that you're calculating to compare what you're seeing experimentally with real world?
So I'm not aware of specific experimental data, but I did heavily utilize this paper here, which is a molecular dynamics simulation, and they actually looked at 4 different systems. And in my actual research, I try to match all 4 of those systems as well. But yeah, I'm not aware of any actual experimental data that I could use to try and fit to, but it would be nice if there was. But yeah, in lieu of that, this is probably the best I could use. Not to mention it's written by a good guy.
I would just comment that in colloid and interface science, the measurement of zeta potential of colloids is a place where you can get really good experimental results. And this is the equivalent of the idea of the zeta potential. So the potential that he's showing in the brush would be analogous to a zeta potential in other experimental methods. Anything else?
I don't know, and it was just.
Yeah, no, it's a raised hand. It says it on the screen.
You could view, I think.
Oh, I don't. Well, Animish?
Yeah, did I hear you right when you talked about the time scale of some of this initial diffusion? Is it something of the order of a nanosecond?
So let me bring the slides back up real quick. And then go back to it. So, obviously there's a lot more going on. I just show 5, time steps here. But yeah, there's between, you see, like, this is almost initial, right? It's just after initial to 0.12 nanoseconds. You could see a big change in concentration. Now, obviously, it's due to all these interactions combined, not just to diffusion, right? But
so these are extraordinary because, extraordinarily fast because the transition of an electron in the triplet state or singlet state is of the order of 0.1 to 10 nanoseconds or something like that, if I'm not mistaken. So here, whole atoms are moving at that speed over 100, approximately 100 atom diameter, right? And presumably some of these atoms also have hydration shells associated with it. That's a lot of speed for a very large stuff.
yeah, so I would say because I started off with a good amount of sodium in the brush region, I think a lot of the majority of the change you're seeing is overall due to the binding that's occurring. But yes, obviously, as this is binding and you see that the magenta line here, there's still a good amount of sodium over here. So it had to come from somewhere. So it comes from the salt region. What plays an impact is these diffusion coefficients. Now, from that molecular dynamics paper, I don't have any real insight into the real values of these. So I tried to choose.
I see. So these are okay. So
I tried to choose what I considered reasonable values based on in the MD paper, they achieved with their starting conditions, they achieved steady state in about 100 nanoseconds according to the paper. And so I tried to I chose these values such that my time scale would be on the order of like, so that, sorry, let me take a step back. When I implement this to solve it, I don't implement this form of the equations. I implement a dimensionless form. And so I chose values of these such that my dimensionless time step was about like, so so like one dimensionless time step corresponded to essentially 0.5 nanoseconds. So that's how I chose these values to get a certain time step.
Yeah, you might re-examine that particular assumption.
Okay.
And it doesn't change your results. The shape of the results would be the same. But I'm worried about the time scale in which you think is happening. These look to me extraordinarily fast, but maybe I'm wrong. I'm not a physical chemist.
I mean, it's good to get other eyes on it because, I don't have, I'm the math guy and I don't necessarily think about those types of things. So it's good to hear something like that. But yeah, I'll definitely take a look into that.
Yeah. Okay.
I want to emphasize the thickness of the brush. This is not the thickness of the glycocalyx that we were looking at. This is based on a model of a very thin layer. It's 60 angstroms, right?
Yeah,
So
roughly.
60 angstroms, 6 nanometers, that's on the order of the size of a bilayer membrane. So that's much, much smaller than the glycocalyx.
But I see Animish's point, and I am a physical chemist, so I'm with you, fractions are that hundreds of thousands of a nanosecond to get across a bilayer for a molecule. It's just, I think you said it right. I mean, you use sort of an arbitrary number to say is nanoseconds. You just have to look at what arbitrary number you use.
It might actually be informative. We use Nernst equation in there, and Nernst equation is used for modeling transfer of ions across plasma membrane. So maybe look at the timescales that are associated with that, considering plasma membrane is about the same, width of the brush that you guys are modeling. So if Nernst equation, which is used for modeling mineral depolarization, works, maybe that time scale is where you look.
Okay.
Anything else? Go ahead, see if anybody online might.
Let's see. No, I don't see any other raised hands.
Okay. Well, thank you, William. Let's give him an applause. Okay. Thank you all for attending today. I really appreciate it. I wish we had time for a panel discussion of some sort. Maybe some other time. I think this was a lot of fun. I'm really enthusiastic about these. All the talks. I think this was a really interesting session, putting a lot of different pieces together regarding these interfaces that are characterized by glycans. And all the biological information we saw today was really great. So thank you to the speakers once more. Let's give them all a round of applause. And we will see you in other meetings online. Thanks for attending today, everybody. Thank you, Sean.
Thank you for arranging this.
Well, I will stop recording. Thank you.